Hello everyone, welcome back to a lecture series on aerospace propulsion. So in the previous lecture we were discussing about the area velocity relation. So from that area velocity relation we were able to mathematically explain how a particular, whether it is a convergent section or divergent section, will be able to act as a nozzle as well as a diffuser. Okay, so in that relation we have seen, like, if the flow entry is subsonic, okay, if the nozzle is convergent, okay, so then, or a passage is convergent, then the flow will be accelerated through that. Suppose instead of subsonic flow, if the supersonic flow enters the convergent section, what will happen is that the flow will be decelerated. Okay, so this will happen opposite in case of divergent section, where the subsonic entry will lead to deceleration and supersonic entry will lead to acceleration. So we have seen, like, the relation between area and the velocity for the subsonic case and supersonic case. For supersonic case, it will behave in opposite manner. That is, if the area is increasing, your velocity will decrease. The area decreases, your velocity will increase. Whereas for your supersonic entry, it will be same. If the area will be increasing, means your velocity also will increase, and area decreases means your velocity also will decrease. So in the same area ratio relation also, we have seen the condition where dA by A is equal to 0. That is, when if your Mach number m is equal to 1, what happens is that your area will be either minimum or maximum in that particular location. Or what is the meaning of this dA by A is equal to 0 for m is equal to 1 is that where the Mach number becomes 1 will be the location. Either it will have the minimum area or maximum area. The maximum area is not possible. Only possible is that at the minimum area location, if you take any passage, if I'm going to say at the in the passage my flow becomes sonic, m is equal to 1, means where it will happen is that at the location where my area is minimum. Okay, so that's what we have discussed in the previous lecture. So today's lecture we are going to discuss about isentropic flow through a convergent nozzle and isentropic flow through a convergent divergent nozzle. So we are going to see what is the Mach number we can generate using the convergent nozzle, and why do we need the convergent divergent nozzle, and what is the meaning of isentropic flow through convergent nozzle and isentropic flow through convergent divergent nozzle. Is that here we are going to assume that flow through my nozzle is isentropic. Okay, you say, how come I can assume my flow through nozzle is isentropic? In sense, you see, the isentropic flow means there are no losses, or the loss happening is of negligible amount. So those type of flow, we say it is the isentropic flow. How do we make, or how do we assume that the flow through nozzle is isentropic? Is that, you see, for the nozzle, the pressure gradient exists in the flow direction is basically favorable pressure gradient. So what is the meaning of favorable pressure gradient? That is, the pressure in the direction of your flow will be keep on decreasing. So if the pressure is keep on decreasing, means what will happen? Your flow will be accelerating. So accelerating means basically your flow is having sufficient momentum. The boundary layer growth happening over your nozzle walls will be very thin and it won't separate. So as you know, flow through passages means one of the major loss will be, one is due to friction, another one is due to the flow separation. So in case of our nozzles, due to the favorable pressure gradient, the flow separation will not occur. So obviously the only loss will be going to be due to friction. So which also we can neglect for our this discussion. So that's why we say the flow through nozzle is isentropic. Okay, so let's start with the isentropic flow through a converging nozzle or convergent nozzle. Okay, so what is a convergent nozzle? A passage in which if the area decreasing, okay, that is dA by A is decreasing, means those type of passage what we call it as the convergent passage. Okay, so what is this convergent passage and how do we establish flow through converging nozzle? Is that, you see, if I'm going to take a nozzle, let's take a convergent nozzle. Usually what will be the input for your nozzle? It is, we have a gas turbine. Let's say where we are using nozzle, basically if you take a gas turbine engine, So where at the after your afterburner or after your turbine, you will have the nozzle. So basically the inlet we are or input we are giving to our nozzle is total flow with certain total pressure and total temperature. Okay, so your velocity will be very negligible at the inlet of your nozzle. Okay, so how do we establish a flow through if I am going to take a passage? How do I make my flow passing through passage? Is that either you have to create the pressure difference between these 2 points, or you have to create the density difference. Either way, either pressure difference or density difference will result in movement of your flow from one place to another place. Let's take a pressure difference. So pressure difference, if I'm going to create either I can, if I want to establish flow in this direction, I can decrease my flow pressure in this flow pressure here, or I can increase my pressure here. There are two ways. One is I can either decrease the pressure in the downstream direction such that the pressure there will be less than the surrounding pressure, so your flow will start moving in this direction, or without changing the downstream location, I can change increase the upstream pressure. That also will create a pressure difference. This pressure difference will make the flow to move in the forward direction. Okay, so now here I'm going to take the case where, let's say my nozzle inlet pressure is P0 and T0. Okay, initially. Now what I'm going to assume is that initially my P0 is equal to PB. What is a PB here? Is basically it is the back pressure. So what is the meaning of back pressure here? Is that it is the basically pressure of the environment to which your nozzle is going to eject the flow. That's what we call it as the back pressure. So here I'm not going to change anything to my P0 and T0. Let's say I'm going to change my back pressure, that is pressure of my environment. But in actual nozzle case, what is happening is that mostly you will have the high total pressure at the inlet, and the outlet will be basically it is the surrounding atmosphere. Or if you take, for example, for the same inlet pressure, if you change the altitude, what will happen? Your back pressure will be decreasing. If you decrease the altitude, your back pressure will be increasing. Okay, so here I'm going to keep my P0 and T0 as constant. I'm just going to change my back pressure. Initially, my P0 is equal to PB. So what does that mean? There is no pressure difference between inlet and the outlet of your nozzle. That means there won't be any flow exist, right? Because, and we see this line is basically it is the change in your pressure. So since there is no flow establishment, so when the flow is accelerated, means what will happen? Your pressure will decrease, your velocity will increase. So since there is no flow is established because the pressure at the inlet and outlet is constant, so there is no change in the pressure. That's why we are getting the straight line. Now, let's say I'm going to reduce my back pressure to some value. So what will happen? We have already seen the flow entering in a convergence section. If the flow entry is subsonic, means what will happen? It will be accelerated. So when I create the pressure difference here, what will happen? Here velocity is very, very less. So you could say this is subsonic. So the flow will be start moving inside, and as your area is decreasing, your flow will be start accelerating. Okay, so because of the acceleration, I can see that from inlet to exit, your pressure is getting decreased. So at the exit, let's say it is giving some subsonic value only. Okay, initially from 0 to, if I'm going to say first for initial pressure difference, let's say I'm going to get around Mach number of 0.3. Now I'm going to further reduce my back pressure. Okay, so for this pressure difference, let's say the pressure velocity I'm going to get or Mach number I'm going to get at the exit of my nozzle is, let's say m is equal to 0.8. So if I'm going to further keep on slowly reducing my pressure for one certain pressure, one certain back pressure, what will happen is that at the exit of my nozzle, I will have m is equal to 1. That is, the Mach number at the exit of your nozzle will become sonic. Okay, so that pressure, back pressure corresponding to which your nozzle exit will produce Mach number m is equal to 1, what we call it as the critical pressure. Okay, so for this critical pressure, what will happen is that the velocity will be keep on increasing, your pressure will decrease, it will have certain value. at the end you will have m is equal to 1 at the exit. Okay, so after this, let's say I'm going to further reduce my back pressure. Okay, so if I'm going to further reduce my back pressure, is that what is going to happen? There won't be any changes happening inside your nozzle. Literally, whatever the pressure you are going to reduce below this P star, let's say P star is corresponding to the value for which I got m is equal to 1 at the nozzle exit. So if I'm going to reduce my pressure below this P star, what will happen is that there won't be any changes happening inside your nozzle. We call them as the frozen flow. Why I am calling it as a frozen flow? Because whatever the changes I am making after P star, the downstream changes I am making, it is not at all affecting the flow through this nozzle. So if there is no change in flow property, means what will happen? For this given P0 and T0, your mass flow rate will achieve maximum. Okay, so this maximum mass flow rate passing through the passage, what we call it as the choked flow or choking condition. What is this choking condition? At the exit or at the throat of your exit of your convergent nozzle or throat of your convergent divergent nozzle, which we are going to discuss, your Mach number m is equal to 1 will be achieved. So once m is equal to 1 achieved, means there won't be any change in your flow property inside this convergent nozzle. So because of that, the mass flow rate will not at all change for the given P0 and T0. Okay, so now you could ask, so mass flow rate is not changing, means that means we can't change the mass flow rate, or can't we increase the mass flow rate, means we can increase or we can change the mass flow rate. As long as I change my P0 and T0, I can change the mass flow rate through this passage. But what I mean for frozen flow is that for the given P0 and T0, once your pressure at the exit becomes equal to the critical pressure, so if I'm going to reduce my pressure even below that, there won't be any changes happening. That's what we call it as the frozen flow condition or choked flow condition. So choked flow means for the given P0 and T0, the mass flow rate at passage becomes maximum. Okay, now you could ask, why even after so you said like if I'm going to create the pressure difference, your flow will be accelerated. Higher the pressure difference, higher the acceleration you will get. That is the normal logic, right? But why I'm not getting the acceleration if I'm going to reduce my P star below this is because, you see, initially when your flow is subsonic, okay, you know that the information propagation in the flow field is basically it's by means of your pressure waves. The pressure waves are sound waves. The sound waves are moving with the speed of sound. A is equal to root of gamma r t. Okay, so since your flow is subsonic, even at the exit subsonic, means what will happen is that your flow will be able to adjust because the information is propagating faster than your flow speed. Because of that, your streamlines will be adjusting. So whatever the changes I'm making in the downstream location will affect the flow field inside this nozzle. But once your Mach number at the throat location or exit location achieved m is equal to 1, what does that mean? M is equal to 1 means your flow speed will be equal to your speed of sound. So information propagation and your flow speed both are having same speed. That means there won't be any information like moving in the upstream direction. Because of that, what will happen? Your streamlines won't be able to adjust. So because of that, there won't be any change in your flow property. That is why once your m is equal to 1 is achieved at the throat location or exit location, your flow becomes kind of frozen for the given P0 and T0. Okay. So this is how we establish the flow through a isentropic flow through the convergent nozzle. Now we are going to see convergent divergent nozzle. So here one conclusion we came to is that the maximum Mach number this convergent nozzle can produce is m is equal to 1. Then how do we generate this supersonic flow? Since this convergent nozzle is capable of only producing Mach number m is equal to 1, how do we produce the convergent divergent nozzle? Supersonic flow is that by means of using the convergent divergent nozzle, CD nozzle or D-level nozzle. So what is the D-level nozzle? Basically it is the person who has first made this convergent divergent nozzle. Okay, so on its name, we call this CD nozzle as the D-level nozzle. Okay, so now in this section, we are going to see how do we establish the supersonic flow through a convergent divergent nozzle. What all the conditions needs to be satisfied. That's what we are going to discuss in this section. Okay, we have already seen the maximum Mach number a convergent nozzle can produce is m is equal to 1. Okay, so if I want to achieve m is greater than 1, okay, what we have to do is that we have seen right from the area ratio relation, if dA by A, if the area is increasing, okay, when a supersonic flow enters through the passage, its Mach number will be increased. So we have already got, we have, let's say, m is equal to 1 at the throat location. It's a kind of sonic. So now if I'm going to attach a divergence section. So what is the meaning of divergence section? Your area is increasing. So we have seen for the supersonic entry, if the area is increasing, what will happen? Your flow will be accelerated. So that means at this throat location, we'll have m is equal to 1. And after by connecting the divergent section, what will happen is that we will be able to get the supersonic flow. So for achieving supersonic flow, that means first you need to have the choking condition at the throat location. That is m is equal to 1 should be achieved 1. So whether m is equal to 1, even if you achieve m is equal to 1 at the throat location, it is not going to guarantee that you will get the supersonic flow at the nozzle exit. So there are other conditions also has to be satisfied if you want to generate the supersonic flow at the end of this convergent divergent nozzle. So now we are going to see how do we establish the supersonic flow through this convergent divergent nozzle. Okay, so now let's take a D-level nozzle or convergent divergent nozzle. As you can see here, we already stated the minimum area location is going to be the throat location. That means the throat location will have the minimum area compared to either inlet or outlet, or in the passage where we are having the minimum area, that area we refer by the throat. Okay, let's say I have a P0 and a T0 at the inlet of my nozzle. Here also what I'm going to do is that I'm going to change the EP here is basically that is the back pressure. Okay, so I'm going to change the back pressure. I'm not going to change my P0 and T0. I'm going to change my back pressure PB or PE at the exit plane of my nozzle. So for the changes, what is happening inside a nozzle, that's what first we are going to discuss. Let's say initially my PE is equal to P0. What is the meaning of PE is equal to P0? The pressure at the inlet of your nozzle, pressure at the outlet or exit of your nozzle, both are same. If the pressure is same, means there won't be any flow, right? That's why there is no changes happening for the case where your P is equal to P0. There is no flow is being established at all. The flow is kind of stagnant. Okay, now let's say I'm going to reduce my PE to PE1 by keeping P0 and T0 as constant. I'm reducing my exit pressure PE to PE1. So if I'm going to reduce it, what will happen? Here your flow is subsonic, right? A subsonic flow entering in the convergence section, what will happen? It will be accelerated. So acceleration means what will happen to your pressure? Your pressure will be decreasing till your throat location. Okay, the pressure decreasing. So after that, what is happening? Your area is increasing. Area increase means what will happen? We have already seen for the subsonic entry, area increase will result in deceleration. So deceleration means what will happen? Once again, your flow velocity will decrease, your pressure will increase. As you can see here, the curve A basically belongs to the back pressure PE1. Okay, initially acceleration. After crossing the throat, your area is increasing, so your flow will be decelerating. Now, let's say I'm going to reduce my pressure to from PE1 to PE2. Now, by reducing the pressure further, I'm creating even more pressure difference between the inlet and exit. So, what will happen? Initially, let's say I have got M is equal to 0.3 at the throat location for PE1. Now, what will happen? M will achieve around let's say I'm getting 0.8. So 0.8 means once again your flow is subsonic. The subsonic flow entering in the divergence section, once again, it will be decelerated, right? So now, let's say I'm going to reduce my pressure PE2 to PE3. So for this PE3, okay, what will happen is that, let's say the Mach number at the exit of throat location achieved M is equal to 1. Okay, so M is equal to 1 it has achieved. So now we made the nozzle to choke. What is the meaning of choking? At the throat location, you will have M is equal to 1. I already, as previously mentioned, choking alone won't give you the supersonic flow at the exit. There are other conditions also has to be satisfied. Now let's say there are two conditions. Okay, if your pressure at the exit is less than your pressure at the throat location, then your flow will be keep on accelerating. At the exit, you will have the supersonic flow. Okay, so for what? If the P is, that is pressure at the exit plane, is less than your throat pressure, what will happen is that your flow will be keep on accelerating. At the end, you will produce the supersonic flow. If not, what will happen is that your flow once again start to, if the pressure at the exit plane is greater than your throat pressure, means what will happen? Your flow won't be accelerating, it will be once again decelerating. So that means there are two conditions has to be satisfied if you want to generate the supersonic flow at the nozzle exit. First is, you should have M is equal to 1 at the throat location, and the second condition is that your exit pressure PE should be less than your PT, that is throat pressure. After satisfying these two conditions only, you will have the supersonic flow at the nozzle exit. So there is a choking. So for the PE3, you got nozzle choking. For your PEC, you got the complete supersonic flow at the exit. So what happens in between, if we have a pressure in between these two ranges, is that if, for example, let's say for PE4, your flow will be accelerating up to a certain limit. After that, what will happen is that you will have the formation of normal shock inside your divergence section. So the normal shock meaning is that up to this location, your flow is being accelerated. That's why your pressure is keep on decreasing. Okay, but this PE4 becomes kind of like the pressure at this location is become greater than the throat location. Means what will happen? Your flow has to be once again decelerated. So deceleration means what will happen? You know, we have two types of waves. One is compression wave, another one is the expansion wave. So you will have deceleration means you will have the formation of compression wave, that is normal shock will be forming inside your nozzle. So as you know, once your flow crossing your normal shock, it will become completely subsonic. So and your pressure also will suddenly increase when it is passing through the normal shock wave. So after that, your flow becomes subsonic. Subsonic means, what does that mean? You are having a divergent section, your flow will be further decelerated. So what will happen is that between this PE3 and this PEC, PE3 is basically, that is the minimum back pressure for which you have the choking or M is equal to 1 at the throat location. Whereas your PEC is the pressure corresponding to which you will have the minimum pressure corresponding to which you will have the supersonic Mach number at the nozzle exit. If you are having the pressure, back pressure in between these range, what will happen is that based on your pressure, suppose if the pressure is here, means you will have this shock wave. So slowly by decreasing the pressure, your shock wave will be moving in the downstream direction. For your PEC, your shock will be completely, normal shock will be completely pushed outside of your nozzle, and you will have the supersonic flow at the nozzle exit. Okay, so that's what. So you can't just by choking the nozzle, you won't be able to produce the supersonic flow. There should be another condition, that is the exit pressure should be less than your throat pressure. Then only you will have the supersonic flow at the nozzle exit. Okay, so in between this range, you will have the normal shock. Once normal shock forms, means once again at the exit of your convergent divergent nozzle, you will have the subsonic flow. But that's not we want. We want the purpose of adding a divergent section after your convergence section is to get the supersonic flow. So that means the back pressure should be sufficient enough to push your shock wave, normal shock wave outside, so that you can have the supersonic flow at the nozzle exit. So, and one more thing is that you see, what is the difference between your A star and ATH here is that its notation itself is having certain meaning. So ATH is direct, you know that it is a throat area. Your A star also is throat area, but if I'm going to use this asterisk symbol, the meaning is that it is the choked nozzle, or the throat is, that particular nozzle is choked. If I'm going to say the throat location by the A star, if I'm going to denote the throat location by the A star, meaning is that the flow through that particular nozzle is choked. If I'm going to simply mention ATH means it is the unchoked nozzle. A star means basically it is the choked nozzle. Okay. So what we have discussed in today's class, we are discussing about the why we are making the isentropic flow assumption for the flow through nozzle, and then we have discussed about the how do we establish the sonic flow through a convergent nozzle, and we have seen the maximum Mach number we can get through a convergent nozzle is m is equal to 1. So if at all you want a supersonic flow, you need to have the convergent divergent nozzle. So without convergent section also, you can't produce the supersonic flow, because you need a convergent section to generate m is equal to 1 flow, or for the choking relation. So once your nozzle is choked, what will happen? Based on your back pressure, your flow will be either accelerated or decelerated. We have seen two cases where PE3 is the pressure corresponding to which, minimum pressure corresponding to which your nozzle is choked. PEC is the minimum back pressure corresponding to which you will have the supersonic flow at the nozzle exit. Okay. So with this, I'll complete this today's lecture.
Like, share and subscribe. Hit the bell icon for more updates.